Modern executives assume immediate access to performance metrics, but in its native state, raw organizational data is chaotic, unpredictable, and entirely unstructured. Business intelligence exists to capture this raw output and organize it, transforming a void of disjointed numbers into actionable information. Through centralized visual displays, these systems synthesize millions of data points into accessible key performance indicators. Management can review instantaneous cash balances, track regional sales metrics, and monitor critical success factors. The risk lies in treating this interface as infallible. A dashboard is a visual output layer. Trusting the strategic forecast it produces requires uncovering the hidden computational pipeline that generates them. To prevent strategic errors, a financial analyst must stop reading the dashboard at face value and start deconstructing the statistical machinery beneath it. The architecture driving these metrics is known as the analytics continuum, a four-tier progression that escalates strictly in mathematical complexity. The foundation is descriptive analytics. This tier relies on standard reporting tools to query historical records, answering the basic question, what happened? The second tier, diagnostic analytics, applies OLAP and visualization tools to interrogate that same historical data. It identifies past patterns to answer, why did it happen? The critical leap occurs at the third tier, predictive analytics. This diagram illustrates the shift from looking backward to looking forward. By applying statistical assumptions and machine learning algorithms to historical data, this tier forecasts what might happen. The continuum culminates in prescriptive analytics. Here, the system determines the exact actions management must take to optimize those predicted outcomes. Moving from descriptive reporting to prescriptive algorithms allows an organization to pivot from analyzing past events to calculating specific paths to reach a target outcome. The engine powering predictive analytics is regression analysis. This is a statistical process used to derive a linear equation that maps the precise relationship between independent and dependent variables. This scatterplot models a simple regression, represented by the formula y equals a plus bx. In this case study, we track a dealership predicting new car sales, y, based on regional disposable income, x. The algorithm calculates a regression line, minimizing the distance between these scattered data points, establishing an accurate prediction model. To measure the strength of this model, analysts calculate the coefficient of determination, or R squared. If the correlation coefficient between income and sales is 0.8, squaring that figure yields an R squared value of 0.64. This metric means exactly 64% of the variation in new car sales can be directly explained by disposable income. The standard error tracks remaining variance, representing the vertical distance between observed data points and the regression line. A smaller gap indicates a tighter fit. This linear relationship is only valid within the relevant range, meaning the span between the smallest and largest observed values in our original dataset. Remember, regression proves correlation, not causality. Extrapolating this linear trend line outside the established relevant range removes the statistical foundation for the forecast, making any resulting strategy speculative. While regression analysis strictly tests variables we already know, data mining takes an exploratory approach. It deploys computational power to search for unexpected relationships hidden across multiple perspectives. Analysts use classification algorithms to sort information into predefined categories, but when the structure of the data is entirely unknown, they use clustering algorithms to let the variables group themselves organically. This network map represents the classic retail anomaly of clustering. Clustering algorithms processing convenience store transactions unexpectedly discovered a strong purchasing link between diapers and beer during late evening hours. Identifying these links requires continuous trial and error. The algorithm iterates repeatedly to determine if an anomaly is an actionable insight or a software glitch. Data mining successfully extracts value because it relies on raw computation to find invisible structural relationships that human intuition would never hypothesize. When the independent variable in a model is time itself, forecasting relies on time series analysis. This method projects future outcomes based strictly on historical rhythms. This raw historical sales graph appears highly erratic, but it's a composite of distinct frequency patterns. Separating the data reveals fixed-period seasonal patterns, multi-year cyclical patterns tied to business cycles, and irregular patterns, unpredictable random spikes, like a sudden snowstorm. The core limitation of time series analysis is the assumption that past conditions will continue. If underlying population dynamics or market variables shift, the historical pattern loses its predictive validity. Failing to decompose time series data correctly creates fatal flaws in predictive analytics, particularly when an irregular random event is misclassified as a sustainable, recurring trend. The complex algorithms and time series models we've explored are computationally precise, but they are entirely worthless if fed duplicated, missing, or corrupted data. This necessitates the ETL process, extracting data from disjointed sources, transforming it into a uniform format, and loading it into a centralized database. Data normalization protocols then scan the elements, removing redundancy to tighten overall data integrity. This entire pipeline is maintained by data governance, the overarching set of rules that ensures the accuracy, consistency, and usability of the consolidated information. By explicitly defining allowable mathematical and logical operations for specific data types, strict governance prevents critical processing errors during the subsequent analysis stages. Structural data governance is the unglamorous bedrock that makes high-level, evidence-based business intelligence possible in the first place. Data analytics operates through 5 rigorous stages. You must define the questions, obtain the data, clean it through the ETL process, analyze it via regression and mining, and finally, communicate the results. Visualizing these results through column reports or dashboards requires careful execution. Analysts must use fact-based, neutral language to ensure upper management is not misled by inappropriate wording or overly aggressive estimates. The data pipeline executes based on rigorous science and computational power. However, correctly interpreting the outputs, recognizing standard errors, and validating anomalies remains an art that relies heavily on analyst expertise. Modern interactive dashboards reflect this synthesis, simultaneously displaying descriptive results of current operations alongside dynamically updating predictive forecasts. Proficient management accountants architect the data governance, monitor the standard error, and translate mathematical realities into actionable corporate strategy.